Okay. So here's where we're at in terms of reactions of alkenes. So we talked about this kind of yesterday. These are the PowerPoint notes from yesterday's folder. So at the end of class, we said a couple things, or I said a couple things. Number one, anytime you have a carbocation intermediate, the reaction will not be stereoselective. And the reason for that is because after you add the electrophile, the plus charge here plus charge, then the nucleophile can add to the top or the bottom, and it'll add 50-50, just like SN1. So you'll end up with 50% of basically the two additions. Now, this is a bad example because it's acyclic, but the one that we did yesterday was to take our double bond and add HCl to that. And so basically what we said was, well, if I add the H from above the ring, then that's my carbocation intermediate that I'm looking at. And it wouldn't matter here if I added the H above or below the ring. It's the same thing. So the chlorine, the chloride, would add 50% above, 50% below, so that I end up with the chlorine adding then 50% bold, 50% dash. And you may see this kind of squiggly line in sapling. What it means is that it's kind of 50-50 each. So the second step looks like SN1, but you might say, well, what would happen if I added the H plus from below the ring so that the H plus was dashed? Well, I'd still end up with the same thing. I'd end up with the chlorine bold and dash. So what I end up forming is 50% cis addition, 50% trans addition. So there is two possible products, or there are two possible products. It's just that the reaction doesn't select. It forms a 50-50 mixture, so it's not selective. And that will happen anytime you have a carbocation. And I'll even go so far as to stretch that out and say, you're not going to get stereoselectivity anytime you have an sp2 hybridized intermediate. Because as long as you have this sp2 intermediate, whether it's a plus charge or even if it's a radical, you're going to get addition 50-50 to the two lobes. So you won't get a chiral product, which isn't quite true, but for this class it is. There are people that have done radical reactions and gotten chiral carbons, but that's another class that's not now, or this year. So sp2 hybridized intermediates, never stereoselect. So that's where we were at the end of yesterday. So there's some big things that we want to think about in terms of rules. The other rule when it comes to regioselectivity is that if one of the two reagents is symmetrical, you won't end up with regioselectivity. Remember, regioselectivity is two structural isomers are possible. One is formed as a majority product. So in this case, this is a symmetrical product. So I would immediately, or a symmetrical reagent. So I'd immediately say, well, it doesn't matter whether the H goes on top or the bottom, I'm going to end up with the same product. So if either of the reagents is symmetrical, you cannot be regioselective. So a lot of times it's easier to remember the cases where you won't have stereoselectivity and you won't have regioselectivity. And we did the reaction yesterday where I made it unsymmetrical by putting an ethyl group and a methyl group. It could be regioselective now, but it isn't, right? Because when I add the H plus, tertiary carbocations, same stability, I'm going to get those two products 50-50. So it could have been regioselective because it was asymmetric, but it's not because of Markovnikov's rule. So you really have to kind of take each problem on its own as to whether it's regio or stereoselective. You can imagine on the next test, not only am I going to ask you to write the products, but I'm also going to ask you, is that reaction regio or stereoselective? And I think there's a set of problems where all I've done is kind of tweaked it. Because I can go methyl hydrogen, then I can go methyl methyl, then I can go methyl ethyl. And those are three different problems with potentially three different answers for everything. Right now it's boring. We got H plus and Cl minus, or H plus Br minus, HBr, HCl, and then we've got H plus H2O. And we also have H plus and an alcohol, right? Because we did that last week. So we need more reactions to make it more interesting, and we're going to get them. So let's go forward here. So that's where we were at the end of class. AntiMarkovnikov product. Was this? I forget if this was on the video from last time. So AntiMarkovnikov, what you do, and these I just downloaded from the Google into PowerPoint, and apparently it doesn't like that, so it left a lot of stuff out, like the other OH group. So this is peroxide. So if you want to do AntiMarkovnikov addition, add HBr and a peroxide. The mechanism completely changes so that you go through this mechanism, and basically what you're doing is you're adding a Br dot, which is what this is, to the double bond, and the mechanism is then based on, well, I can add the Br dot to each one of these two carbons. Which radical then do I form that's more stable? And so in this case, the tertiary radical is going to be formed, and it's more stable, and that's where the H gets added to. So the mechanism completely changes. So could that reaction be regioselective? Sure. It's anti-Markovnikov. Could it be stereoselective? No, why not? Because it goes through an sp2 intermediate, the radical. So this one could be it could be regioselective, but it can't be stereoselective. So that's something different. It's just we're applying Markovnikov's rule, even though the reaction doesn't go by Markovnikov addition. I'm again going to broaden this out. Markovnikov addition is when you add an electrophile to the double bond. So something plus gets added to the double bond, and then something negative adds after that. So this is not a Markovnikov reaction. The product is not the one you would predict from Markovnikov's rule, therefore we call it anti-Markovnikov. So again, it went through that. Then bromination. Was bromination on the video for yesterday? Okay, so bromination could be stereoselective. This is the first of a bunch of reactions that involve a triangular intermediate. So we think of the Br2 as really kind of breaking apart and forming a Br plus and a Br minus. And you might say, but that's not going to happen because they have the same electronegativity. Yes, that's true. What happens is the double bond approaches the Br2, and the electrons from the double bond kind of polarize one of the bromines to become slightly positive, and the other one becomes slightly negative. Now, bromine plus, a Br plus, is big enough to sit on top of both carbons of the double bond. H plus was not big enough to do that. H plus kind of chooses which carbon it's going to bond to. It really can't sit over both carbons for any length of time. Now, if you're going, yeah, but I've written that transition state when the hydrogen is migrating from one carbon to the other, it's a transition state. It's very high energy. The hydrogen never sits there for any amount of time. If it did, we would get stereoselectivity for double bonds. For HCl addition, it would be stereoselective if the hydrogen sat there and formed a triangle. If we don't get stereoselectivity, it doesn't happen. But for bromine, we do. That was the first thing that somebody noticed. When they did bromination, they found out that the bromine added trans. How would you know that? You would know that by doing the reaction with a cyclic system. So when they did it with the cyclic system, they noticed the only product they ever got was the two bromines adding trans. So then probably 30 years later, somebody figured out what the mechanism was. And the mechanism is for the bromine to basically sit over both carbons. That forces the other bromine to come in and add from the bottom. And so it shifts over. Something similar to that is mercuration, demercuration. Was that in the video too? So the mercuration, demercuration, basically what happens is I make, and besides all of this crap, I make an HgOAc plus. So we start with mercury 2 plus, and we lose an acetate. So the acetate was, I probably drew this in the video, but an acetate is a deprotonated acetic acid. So that's what the OAC stands for. It's deprotonated acetic acid. So when I lose, I've got an Hg2 plus with two counterions. I lose a counterion, I make an Hg plus. The Hg plus is big enough to sit over both carbons in the double bond. And so what happens is that basically my carbon is partially bonded to the mercury. Both carbons are partially bonded. And what that does is that spreads out the plus charge to both carbons. So neither one of them has to take on the full burden of the +1 charge because the mercury is sitting over the top. So we have another triangular intermediate, like bromonium ion. With the mercury sitting over the top, it forces stereoselectivity. Or it can force stereoselectivity. Meaning that in the next step, what I ended up doing was I ended up adding water to that merconium ion. And so then the water can add underneath so that I end up with, over here, let's say, in the end, the OH adding opposite the mercury. So I get trans addition. As I went through in the video, that's 2 steps, right? Whole water comes in, adds, makes an oxonium ion. I lose H plus to give me the OH, but I form that compound. So the OH and the mercury added trans. And then in order to convert the mercury to a hydrogen, we add sodium borohydride, which is a source of H minus. And we know from the final product that the H minus of the sodium borohydride replaces the mercury in exactly the same spot that it started. So that in the end, we've got the H and the OH here have added trans. So actually this one should be, it shouldn't be that. It should look like this. The H and the OH added trans. Okay, so bromination and mercuration, demercuration are basically the same kind of mechanism. They undergo an intermediate that's triangular. Anytime you have a triangular intermediate, the 2 groups will end up adding trans to each other. That's a basic principle. So anytime that electrophile sits on top, forms a triangle, you have trans addition. In this case, the mercury ends up adding to the carbon with the most hydrogens. And the OH ends up on the carbon that's most substituted. Okay. And if I remember correctly, this is about where the video ended. And I didn't do anything with this, right? I did? What did I do with it? Okay. So I'm going to go back, and this is where I'm going to kind of start here. So let's talk about regioselectivity then. Let's talk about regioselectivity in the context of the triangle, because that's what I need to talk about. So what I need is a blank slide. Blank slide. There. So if I'm let's see. I'm going to take a double bond here. And I'm going to add my HG OAC plus to that. Okay, so I'm going to start with that. So let's do this without the triangle. I'll put 2 methyl groups here, and I'll put 2 hydrogens here. So let's make this asymmetric. So now let's add the mercury without the triangle. So let's make a choice. Let's add the mercury to carbon A, and let's add the mercury to carbon B. So if I add the mercury to carbon A, it's going to look like this. And I'm going to leave the plus charge then. The plus charge is going to go on the CH2. Okay, so I'm basically going to add the HG OAC group plus and that's going to be my electrophile. So if I add the electrophile to carbon A, I end up with that carbocation. Right? Same thing as if I added H plus to carbon A. And if I add the mercury to carbon B, I'm going to end up with that carbocation. Everybody kind of with me? So all I did was just, I eliminated the triangle for the moment. So if we're looking at regioselectivity, which carbon did I add the mercury to? Which carbon would, if the mercury had to make a choice of adding to only one of the carbons, and remember it doesn't, it sits over the top. But if it had to make a choice, which carbon would it bond to? A or B? Give me an answer. Somebody just shout out an answer. B? So the mercury would add to B. No? No? We don't like B? Which one's it going to add to, A or B?
A.
A? I don't like A. Anybody else like A? I don't like A either. I already said that. How do I know that? This seems like deja vu. We're explaining Markovnikov's rule. So I'm going to add the electrophile to A and B. Which one does it add to? The one that forms the most stable carbocation. What kind of carbocation is the first one? This one is primary. What kind is this? Tertiary. So which one is it going to choose? Where's the mercury going to add? Where's the mercury going to add? The mercury is going to add to form the more stable carbocation. Where did the mercury add here? It added to B. Right? Carbocation is a tertiary carbocation versus primary. I'm not even allowed to write that, am I? John?
So the mercury adds to the carbon. It doesn't add to the most stable carbocation. It adds to
the carbon. It adds to the carbon with the most hydrogens.
Right. Is it because it's the electrophile?
Yes. So I'm treating the Hg plus OAC as if it was an electrophile. So I'm actually treating it as if it was an H plus in this case. Here's what I need to build. Here's what I need to build to. I need to build to how do you deal with regioselectivity in a triangle? Because we've talked about regioselectivity here. If you choose a carbon to add the electrophile to, you have two choices. It's going to add to the carbon that gives you the most stable carbocation. Are we all agreed now that's going to be B? So if it adds to B, it gives me a tertiary carbocation. If it adds to A, it gives me a primary carbocation. So it isn't going to add to A. And I'm treating the Hg plus as if it was an H plus. I'm treating it as if it's any plus. So that means that I would form this intermediate, and where would my water add? It would add to the carbocation. So in the end, what product would I make? I would have
the CH3, I would add the water to carbon A, and I would have the mercury, which was my electrophile, on carbon B. So that's the intermediate that I would make. I added the whole water molecule this time. I'm writing the explicit mechanism, like I would ask you to do. So we would add the water, and then I would lose H+, so that now I would have my CH3s, I would have my OH, and then over here I would have my mercury acetate. And this is exactly what I wrote on the previous slide. So this is Markovnikov addition. I added the electrophile to the carbon with the most hydrogens, did I not? Right? I added it to the carbon with the most hydrogens, which was carbon B. It's just now I've got a different electrophile than H+. Where did my nucleophile add? My nucleophile added to the most substituted carbon. Why? Because I formed the more stable carbocation. Okay. Does that make sense to everybody? Now, does this happen? Does it happen this way? No. How do I know that? Because if it happened this way, what would happen to the mercury and the OH? I would get 50-50 of them adding cis and trans. And the reaction would not be stereoselective, but the reaction is stereoselective. So this is not the way it works. What does it go through? The triangle. The triangle is great. The triangle is great for explaining stereoselectivity. It's great for explaining stereoselectivity, but how does it explain regioselectivity? There's my triangle. The positive charge is spread out over both carbons. Because the mercury is big enough to sit over both of them. By spreading out the charges, it actually is a little more stable because each carbon then gets a little bit of the positive charge and nobody has to bear the brunt of a full positive one charge. It shares. So you're the water molecule, and you need to add from underneath. You need to add to one of those two carbons. Which carbon are you going to add to? Choose one. Can't be both. Carbon what? Carbon A. How many people agree that it's going to add to carbon A? Anybody think it's going to add to carbon B? No? Nobody wants to go for carbon B? It wouldn't be wise to go for carbon B. Because what did we just say on the last slide? It's carbon A. Right? But sometimes when I do this, we don't go through the first step. I just throw this up there and I say, which carbon do you want to add to? And people will say, well, I want to add to carbon B. And they will say, well, give me a reason why you would want to add to carbon B. You'd want to add to the carbon on the right. What would be a reason that somebody would say, a wrong reason, but a reason nonetheless, that they would add to carbon B? Anybody have a reason why you might want to go for carbon B? You're not going to be wrong. You're just proposing the reason why. Rebecca? Less steric hindrance. So it's less sterically hindered to add to B than it is to add to A. That makes sense, doesn't it? Maybe it's not wrong. But that makes sense. It's A is less sterically hindered, or B is less sterically hindered than A. And to further somebody's argument that that would be the case, am I not kind of doing a backside attack here? That the water's coming in and kicking off the mercury from underneath? So it's kind of doing a backside attack? So when you think backside attack, what mechanism do we think? SN2. So what sterics are in play with an SN2 reaction? The ones that react the fastest are the ones that are least sterically hindered, that are primary. So we look at this, and it has some characteristics of SN2, doesn't it? Backside attack, maybe sterics. But wait, now I'm totally confused because we just went through this whole analysis on the previous slide that said it added to A, right? The water added to A. Well, so what is water? A neutral nucleophile. What kind of reaction does water undergo? SN1. What dictates that water has to undergo SN1? It's a weak nucleophile. It needs the strongest electrophile possible. So in this reaction, we're looking at this as if it was an SN1 with a backside attack. Which carbon? Well, water's going to add to what kinds of carbons? Carbocations. In SN1 reactions, what carbocations react the fastest? Tertiaries. Right? Because they can handle the greatest delta positive. They can handle the greatest positive one charge. So the water is going to react with the carbon that is most delta positive. The one with the greatest delta positive charge. Because this mechanism looks more like SN1 at this point. Okay? So, water is going to react with the carbon that has the greatest delta plus charge. Which carbon is that? Okay. Yes, A. What took so long? We know it's adding to A, right? We just did this whole analysis that said it's adding to A. So which carbon has the most delta positive charge? The one that it adds to. Well, I understand your hesitation here. Why does carbon A have the most delta positive charge? Because it's tertiary. Let's put quotes around that. It's not really tertiary, right? But it looks like it's tertiary. Right? This looks like a tertiary. This one looks like a primary carbocation. So that carbon that's tertiary will be able to have more delta positive charge. Why? Well, because the methyl groups are able to stabilize it a little bit more. Actually, this one, if you did this on the computer, it wouldn't actually look like a triangle that's perfectly symmetrical. It would look more like a triangle like this, a right angle triangle, because actually the mercury would be mostly over carbon B, and it would be far away from carbon A, because carbon A can kind of hang by itself because it's tertiary. It can handle the positive charge. Now there would be enough of a bond there with the mercury to force the water to add underneath. So when we look at a triangular intermediate, particularly with a weak nucleophile like water, you have to look at the carbon that is most delta positive. So sterics don't play a role in this kind of reaction. Now they will later, but not right at the moment. Anytime you've added a plus charge to a double bond and those two carbons have delta plus charges that add up to 1 plus 1, the nucleophile will always add to the carbon with the most delta plus charge. And that's just the one that looks like a tertiary or looks like a secondary overlooking like a primary. So this is how we place regioselectivity in the context of the triangle. Does that kind of make sense? So, now this thing's totally messed up. So mercuration, demercuration, I don't know if I did alkoxymercuration. All I did was change HOH to ROH. So now I've added an H and an OR across the double bond. How have I added it? So alkoxymercuration, demercuration, you're adding the mercury and alcohol, followed by sodium borohydride. What am I adding? An H and an OR. How? Markovnikov. How? Triangular intermediate of the mercury means they've added trans. So alkoxymercuration, what am I adding? H, OH. How? Markovnikov. How? Trans. Remember, this all boils down to those three questions for every single reaction. HBr and peroxide, what am I adding? HBr and peroxide. I'm adding H and Br. How? Markovnikov, anti-Markovnikov. Anti-Markovnikov, cis-trans. This is HBr, peroxide. If it was, we'd be moving on.
Oh, they're not trans. I just wrote that down like 5 minutes ago.
It was actually, that was a little bit longer than 5 minutes ago. But here's our HBr. Here's our HBr and peroxide. It's this one. So it goes through the radical intermediate. So radical intermediate means sp2 hybridized intermediate. Means that it always adds 50-50. Carbocation, radical intermediates, always 50-50. So HBr, I went back to HBr and peroxide. HBr, AntiMarkovnikov, 50-50. Br2, right? Br2, what am I adding? 2 BRs. Markovnikov or anti-Markovnikov? Doesn't matter, it's 2 BRs, right? Can BR2 addition be regioselective? Can BR2 addition be regioselective? No, why not? Regioselective. I'm adding the same group. Symmetrical reagent. BR2 symmetrical. Doesn't matter whether I add the BRs this way or this way. I'm adding 1 BR here, 1 BR there. So BR2 addition, there's no Markovnikov or anti-Markovnikov. Now, I'm going to change that and then we'll go Markovnikov. But right now, 2 BRs, symmetrical reagent, can't be regioselective. BR2 addition, cis trans, 100% trans. Okay, these are the things that you have to know for each reaction. So if it goes through a triangular intermediate, it could be stereoselective. So then I would think that the next one would be formation of bromohydras. And I think this is new. But it's not. So, a bromohydrin is when you add a Br and an OH across the double bond. That's a bromohydrin. So the way that you get a Br and an OH across the double bond is to add Br2 and water. And usually there's an excess of water. So what happens in this case? Basically the Br becomes a Br2 becomes a Br plus, and we form our bromonium ion. So the Br plus, and that's the only thing in there that can be an electrophile. The double bond comes up and interacts with the bromine. The bromine that it's closest to becomes delta positive. The Br then the other Br becomes negative. So we have a Br plus, we have an electrophile to add to the double bond. Br plus is big enough to bridge the gap, so it forms a triangle. But if I do this reaction with Br2 and water, and a large excess of water, if we think about the mechanism, before the Br minus that would form had to go all the way underneath and add. Well, if you do this with Br2 and water, when I form this Br plus, there's already an H2O molecule underneath there that will immediately add. And so the H2O will add. I'll end up with an oxonium ion, and my Br will slide over. And then from my oxonium ion, I lose H plus to then give me the bromohydrin. And so I end up with this bromonium ion, where there's actually a Br there, and there's no delta plus there. So Br2 in water looks an awful lot like if I'm going to add the Br plus to the double bond and form this intermediate, and then I'm going to write my water down here. And it's going to add to the triangle. If you're the water molecule, which carbon are you going to add to, A or B? A, that was fast. Thank goodness that was fast. Right? Because we just do this whole thing, except the Br plus wasn't a Br plus, it was an Hg plus. Right? So it's the same thing. The Br plus, it's over there. The water comes in, it's going to add to the carbon with the most delta plus charge, which is A, because in this case it's the same molecule I just gave you, which is tertiary. So the bromohydrin reaction is exactly like the mercuration demercuration, which is kind of like the Br2 addition. I'm adding a big E plus. It is sitting over the carbons. The nucleophile is going to add to the carbon that's most substituted. In the end, what that means is the electrophile ended up on the carbon with the most hydrogens, and the nucleophile ended up on the most substituted carbon. And as I think I said a while ago, but not that long ago, within the last hour, I broadened my definition of Markovnikov addition to now say the carbon with the most hydrogens gets the electrophile, the most substituted carbon gets the nucleophile. But now I'm not strictly limited to H plus. Now I could use Br plus or mercury plus. So same thing would happen here with the triangle. The water is going to add to the carbon. But I know this reaction goes through a triangular intermediate because the Br and the OH always add trans. So for this one, what am I adding? A Br and an OH. How am I adding it? Markovnikov, my new expanded definition of Markovnikov. And how am I adding it? 100% trans. Could the reaction be regioselective? Well, reactions could be regioselective if they follow Markovnikov or AntiMarkovnikov. Now remember, if it's a symmetrical reagent, not regioselective. But it could be. Stereoselectivity. Could be stereoselective in this case. Why? Because I'm adding my two things trans. And I have to use the phrase could because in a cyclic system, you would be able to see the Br and the OH adding trans. In an acyclic system, right, if I just have the double bond that's flat with no ring to accompany it, where did the Br plus add? Did it add to top face? Maybe. Did it add the bottom face? Probably, 50-50. And so then when the OH adds, I don't necessarily could end up with stereoselectivity. Then I have to go back to what I said probably yesterday, sometime in the last 5 days. We'll have to talk more about stereoselectivity because here's the thing. To be stereoselective, you have to make a product with two chiral centers now. You're just going like, why not one? Because remember yesterday we said that unless you have a chiral reagent, you can't pick one of two enantiomers. So if you make a product with only one chiral center, you can't pick R or S. So you need at least two chiral centers, because then you're going to have picking one diastereomer over the other. So like I said, we could do a ton of these problems, and we will, but every time I change something, I can potentially make it a different problem. And you'll have to do that for the next test. So that's what we'll do. So when we get back Monday-ish, well, I have to say ish because people might take an extra day like they did today. Although this isn't bad, I would probably take an under and been wrong. What we'll do is I'll still be lecturing on this when I get back. So there's nothing to do if you want to get ahead on sapling. You need some away from family time. Feel free to get ahead.